Okay, hello everyone. I have shared my slides, so I hope you guys can see the screen and you can hear me clearly. If not, let me know. So today we are going to start a new discussion, a new chapter of the book, which is basically about the I/O ports in AVR. Actually, we have been using I/O ports right from like the first lab. So we have used them in coding, but we haven't talked about them in detail, right? So for example, we have used the data direction register or port register, but we haven't talked about different instructions which can be used specific for these ports, or not really specific, but we haven't talked about purpose of the each register. So we are going to do that today. So we are going to talk about the AVR pinout, which we have seen already, but we will basically focus more on the structure of the input-output pins and how we can do the I/O programming, which basically mean how to read an input from from an external signal and how to send an output. And then also we will have a look at the instructions which manipulate bits instead of the full register like bits of a given register. So just give me. So if we look at Mega 328P microcontroller, we have three different ports, three different I/O ports, and then with respect to each port, we have three registers. So three registers are used to like when you want to do input or output operation on one of those ports. So for example, you have these three registers, pin B, DDRb, and port B registers. All of them are associated with port B. Next three registers, they are associated with port C, and the next three port pin D, DDRd, and port D are associated with port D register. So here you can see basically in the first column their IO address, and this is their memory address. So IO address basically mean like in the IO range, what is their relative address, and this is their absolute memory address, right? All of them are all of these registers which are associated with these three ports, all of them are 8-bit wide. One thing which you need to note is that port C is 7-bit on at Mega 328P. So what does it mean? On one side, we are saying that the all the registers are 8-bit wide, but then we are also saying that the port C is 7-bit. So it basically means that you have 7 physical pins on the chip. So like from PC0 to PC6, not PC7. There is no PC7 on at Mega 328P microcontroller. Uh, this is different from the port B and port D, all of which have 8 pins on the available on the chip. Also, this microcontroller which we are using, it has I/O ports B, C, and D. There is no port A. However, there are other versions of at Mega microcontroller, for example, at Mega 32, which are others which provide all 4 ports or even more than 4, right, up to F. So but on this version you don't have port A, so you have only port B, C, and D, and port C is 7-bit wide in like number of in terms of number of pins available on the chip, and port B and D, both of them are 8-bit wide. But internal registers which are associated with each port, all of them are 8-bit wide. Okay, so here we have this Mega 32 register. Note that it is not the same register which we are sorry, not the same microcontroller which we are using in our lab. So it has 40 pins. One which we are using in the labs, it has 28 pins. So that's why this one has this one has 4 ports. Like for example, here you have port A and port B, and here you can see the 8 pins for port C and then 8 pins for port D. But irrespective of like how many physical ports are available or pins are available on the chip, there are some vital connections which we need to keep in mind. Uh, for our purpose, they are not like super critical. Why? Because we are using Arduino IDE board, which has already which has a printed circuit board, and all the connections are already made. For example, you don't need to manually make a connection of the microcontroller chip with the power supply or with the ground, because that is already done on the Arduino board. But in case like where you don't have the Arduino board, or you don't want to use the Arduino board, and you want to like develop your own circuit, so then you need to like take care of these minimum vital pins, so which is basically providing power and ground inputs. The other thing is like on pin 12 and 13, you need to connect the crystal, which serves as a clock source for your microcontroller. Then your pin 9, it acts as a reset signal. So reset signal, basically its job is when you press it, it will start executing the program from the start, like from the zero location of your program memory. And then other pins which we are going to cover in this lecture are pins related to port A, port B, and C and D, which I have already shown. But again, port A is not available on Atmega 328P, 328P. Okay. There are some other pins which are basically related with the functionality of analog to digital converter, but we are not going to cover them at this in this lecture. But when we will have a lecture about ADC or analog to digital conversion, then we will talk about them. But again, all of these connections are already made on the Arduino board, and you don't need to worry about them if you are using Arduino board. So remember we said that each port has internally 3 registers associated with it. For example, if we talk about port B0, port B, which has 8 pins, port B0 to port B7. So internally it has 3 registers associated with each DDRB, port B, and pin B register. We will talk about them, what about their functionality in upcoming slides. But just keep in mind that every port has its own register. So for example, if you have port A, then you will also have 3 registers associated with internal 3 registers associated with the port B, port A. Okay. And together, these 3 registers, they control the functionality of the corresponding pins. So for example, here X means X can be anything. For example, it can be A, B, C, or D. So in case of like Atmega 328P, X can be B, C, and D, because there is no port A, right? So you will have DDRB, port B, pin B register, and same for C and D ports. So what is the role of then DDR register? So DDR register, actually DDR stands for data direction register. So it's from its name that it is used to control the direction of the port. So direction of the associated port. So it means like if we are talking about DDRA register, so you can use this register to set whether the port A will be used as an input port or as an output port. Okay. So it determines the direction of a corresponding IO port, and you have registers DDR A, B, C, and D for IO ports A, B, C, and D. So when the value of any DDR register and any bit within that, so all of this register is 8-bit, right? So if any bit within that register is set equal to 1, it's mean, so if you set the nth bit equal to 1, it's mean you want to use the nth pin of corresponding IO port as output pin. And if you set the nth pin of a data direction register equal to 0, it's mean you want to use the nth pin of the IO port register as input pin. So let me quickly make this correction here. I forgot to put an X here. So if you have any questions, please stop me. What is the role of port X and pin X registers in outputting data? The role of DDR register, we have already discussed what is its role in outputting data. You need to set the DDR S register equal to 1 for the corresponding pins. So for example, if you want to, for any port X, you want to use all 8 pins as output pins, so you need to write 0xFF. And you have done this in your labs, right? So, but we have not discussed PORTx and PINx registers in the detail. Actually, we have not used PINx register at all before, but we have used the PORTx registers like port B or port C, but we haven't uh, discussed some other functionalities for that register. So PORTx, it is used to hold the data. So if you have configured the DDR register to specify that you want to use this port as an output, then the port X register, the port register of that corresponding port, it will be used to hold the data which will be delivered on the physical pins of the corresponding IO port on the chip. Uh, and the same output which you are like putting in port register, it will become available on the physical pins of the corresponding IO port, but uh, it will also be available or it will be placed in the pin X register. So basically the pin X stands for port input register. So like port and input, so they just like combine them together to make the word pin. So this is how it works. So here you have, let's say you have configured DDRx in the output port in output direction. So here you have a buffer, and this buffer has a control signal which is named as which acts as enable or disable for the buffer. So if the DDRx dot n, like let's say here you want to use port B, DDRB. It's difficult to write. Okay, yeah, give me 1 minute. So let's say you want to say DDRB dot and dot, let's say 1. So you are saying that this is the signal coming from the bit at index 1 of the data direction register B. So and it is now used as the control signal for the buffer. So it acts as an enable signal. So if it is 1, buffer will allow whatever you provide that input to become available on the output. But if it is 0, so then buffer will not allow the input to become available or appear on the output, right? So what is the input? The input is the port X register. So here, like for example, you can say port B dot 1, right? Here, port B dot 1. So whatever is on the is the input. If it is set as 1, this DDR register bit is set as 1. It will become available on the output or on the physical pin of the microcontroller. But then at the same time, that value which you are writing on the output pin will also be placed in the nth bit of the pin B register. Okay. So if you read this register, you will get the same value which you have written in the port B register. But only when you have configured this pin as the output pin. Okay. Uh, okay, so what is the role of your port X and pin X register in inputting the data? So this is the case when you set the data direction register of a port to 00, all zeros. So the first thing is that the data that is read from pins, physical pins, it is placed in the pin X register, like for example, pin B register, right? The other thing is, so this is the role of your pin X register. Now, what is the role of port X register in the case that you have configured the port as the input? So it enables when the value of the port X like X here can be like anything like port B. So if the value is 1, it will enable the internal pull-up resistors on physical pins of the corresponding IO ports, and if the value is 0, then it will disable the internal pull-up resistors, right? So this is like how you can visualize it. So let's say that you have configured here for X I'm using B, right? And let's say I'm setting n equal to 1, right? So basically I'm saying that I have configured the pin 1 of port B as input pin, right? So I have set 0 for that. Now the value whatever value I will read from outside of the AVR chip on the physical pin, that value will be latched or saved in the uh, pin B register, but in its bit number 1. Okay, bit at index 1. And this value, which you whatever you value placed in here, it is actually used to control this switch. So for example, if the value, let's say the value of port B dot 1 is 1, then the switch will be closed. But if the value of this port B dot 1 bit is 0, then the switch will be open. And this is known as a pull up. This is a pull up resistor. So so if it is 1, then the pull up resistor will be connected. If not, then it will be act as an open circuit, right? Then any questions here? Then you can ask the question that why there are internal pull-up resistors on IO pins, why we need this resistor, why can't we simply connect directly this input pin to the PINx, and why the AVR puts this internal pull-up resistor. So the issue is that when the external logic, which basically mean the external input is 0, 0 is placed on the input, so that 0 will be latched into this bit of the, let's say, pin B register, nth bit of the pin B register. And when the external input is 1, the 1 will be latched uh, in this bit of the pin B register, right? So that's fine. So the problem becomes that when there is no external input provided, but the pin itself is configured as input. So if no external input is provided, then what will become available here in this pin? It can become undeterministic if we don't have pull-up resistor. Why? Because if we don't have pull-up resistor, then the input pin is floating. So input pin is floating mean like you don't it is not connected, it is not stable, like what voltage is read here when you are not providing any external input. And the voltage which is the logical value placed in this internal register pin, let's say pin B dot 1, it can be randomly logic 0 or logic 1 due to noise or an unwanted interruption, right? So that's why what we do is, actually we don't do it, but the designer of the AVR microcontroller, they have already internally fabricated this resistor, pull-up resistor. So if this pull up, but we can only enable or disable this resistor. And but if we enable it, so what happens that now this connection will be made. And even when we don't provide any, let's say if we don't provide any input, so we will have the VCC connected through this resistor, and we will have a voltage here, right? So this is a low value resistor like 5 to 20 ohm something. So that's why we by default we have logic 1. So whenever we have an external input of 0, so 0 overrides 1, and it will become 0, and we will read 0 in the pin B dot n. Whenever external input is 1, we will have pin B 1 in the pin B dot n bit. But when there is no input, external input placed on the pin, we will not have any random signal. We will always know that the value will be 1 whenever there is no external input. Okay, so these pull-up resistors are basically used to provide the stability stability for the external inputs logic or external input values. Any questions? Okay, the one thing is, like we said, that the AVR microcontroller has already built this internal resistor, so we don't need to worry about that. However, we can enable or disable this pull-up resistor. When we can enable or disable pull-up resistor only when a port is configured as in input mode. So if it is configured as in input mode, then we can decide whether to use this pull-up resistor or not, right? And how? By putting the value of 1 or 0 in the corresponding port register. Like let's say we are saying port B, so then if we put port B dot 1 in if we put 1 in port B dot 1, then what will happen, that the internal pull-up resistor on the pin 1 of the port B will be enabled. Okay, any questions? Okay, so based on our discussion so far, any port of the any pin of a port on the microcontroller, it can be in one of the four states. So depending upon what are the values you have placed in the DDRx register and the port X register. So for example, let's say instead in place of X, I am using B. So let's say keep our discussion like more concrete. So DDRB and port B. So like if you have placed one, then it's mean you are using that port in output mode, right? And if you put, so here it means the output mode, but if you put value 0, then it will mean that you are writing 0 on that output line. And if you are putting 1 in this port B, it's mean you are putting, you are writing 1 on the you are outputting 1 on the on that line or on that port, right? The other thing is like if you are using if you put 0 in the port in the DDRB register, so it's mean you want to use the port B in input mode. But again, if you write 0 in the corresponding port B register, it's mean that yes, the port is configured as input pin, but pull-up registers are not enabled. So which basically mean that here the switch is open, right? So and it's mean that we see a high impedance or open circuit, right? And if your DDRB register, let's say set equal to 0, it's mean we are still using the port as input port. But now if we look at the value of the port B register, for example, if it is set equal to 1, then it's mean that yes, it is still using as input port, but the pull-up registers are enabled. Okay. And it is like in most of the conditions, for example, when you are not dealing with ADC or analog to digital conversion, uh, other than ADC, it is preferable to use the pull-up resistors because then it provides you stability in your input. Okay, any questions? Okay, so now let's start using the knowledge which we have gathered until at this point in our assembly programs. So let's say we want to write a program that sends 1 to all the pins of port B. Okay, so it should be trivial because you have done, I think, multiple time the similar task in your labs. So let me walk you through the first one. First example, so since we want to send one to all the pins of the port B, it's mean basically we want to use the port B as output pin, right? As output port. So first what we need to do is we need to configure its direction. How? By writing all ones in the direction register B, right? And once done with that, after that, what we can do is that we can write all ones in the port B register, and they will become available on these pins. So we will see on this one on these pins. So for example, if you have LEDs connected with this pin, you will see that they will turn on. So here is the code. So you are first loading 0xFF in R20 and you are writing R20 into port B. So actually you are setting all ones in this register, but you are not yet done. You need to also set the direction by writing all ones in the DDRB register, right? Note that if you don't set DDRB register by writing 0xFF, then you will not see the high logic available on the physical pins. Yes, you have written already the value here in port B register, but this port B register will not, value of this port B register will not become available on physical pins. Remember, uh, let me go back. Yeah, remember we see that there is a buffer and this buffer has a control signal which it enables or disables it, and it is enabled when this DDRx register its value is 1. So until you write 1, this input will not become available or it will not appear on the output. When you will write 1, then only after that it will become available. So actually in like I guess in lab 3, when I was preparing the lab 3, so I was making this mistake that I was not setting the DDRB register. Actually, I was setting it, but the execution control from the C or from .inf file, it was entering into the assembly file at a point before that where I was setting the DDRB. So actually it was not executed. It was never executed. And as a result, what was happening that uh, my LEDs, they were not switching on. So I was like, what is wrong? And I spent like I don't know 1 hour to figure it out, and then I realized, oh, I am putting the label at the wrong place. Okay, so the point what I'm trying to say is like you must enable the direction register, configure the direction register. Otherwise, if you are writing value into port B, it will not appear on your output physical pins. Any questions? Okay, let me check the time. Yeah, okay. So, example two, you need to write a program which toggles an 8-bit pattern of port B forever with a time delay between on and off states. So, what we want to do is like, you first want to send alternative bit pattern of 0 1 0 1 0 1 0 1 to port B, and then you want to send the pattern of 1 0 1 0 1 0, but you want to put a delay between between sending these two patterns. And since you are writing on all the pins, sometime 1 and sometime 0, so you need to configure all the pins as output pins, right? So okay, uh, can you please try writing the code for this example? It should be easy. Uh, you have 2 minutes to do that. Try writing on your notebooks and let me know when you are done. Is everyone clear on what you are supposed to do? It's pretty straightforward. You just need to first send pattern of alternative 0 1 0 1 to the port B, then put some delay, and then send a pattern of 1 0 1 0 on the physical pins of the port B, right? When done, please send me a text or you can unmute yourself. Anyone who has written the code? Okay, then let me let me walk you through. So first thing is like since we want to put all ones in DDRB, but we cannot directly write in DDRB register, so we can load 0xFF, which is simply hex form of 8-bit binary for all ones. So we are loading it into R16 register, and then we are sending that R16 register to the output port, not output port, to the DDRB register, right? So by this, we are configuring the port B in output mode, all the pins, right? And then we are loading 0x55, which is hexadecimal form of this bit pattern, first bit pattern, right? We are writing in R16, and then we are sending, we are writing R16 on the port B. So now it means that if we, let's say if we have LED, 8 LEDs connected, now LED 0, 2, 4, and sorry, 4 and 6, they will be switched on. Then we are putting some delay, and we are calling a delay function, which is not written here, but we are assuming, let's say we already have the code for that function. And after that, we are writing the bit pattern of second bit pattern, which has hexadecimal form of 0xa in R16, and then sending R16 to the port B register. So now we will see that our LED 1, LED 3, LED 5, and LED 7 are turned on. And then we are putting some delay, and then we are going back to the L1, and we keep doing that forever. Any questions? Okay, so here we have another example where of like using a port in output mode. So let's say we have a 7 segment LED which is connected to the port C of the microcontroller, and we want to display one on that 7 segment LED. So before we go to the code, just know it that this 7 segment basically consists of 7 LEDs, and they are numbered as or they are addressed as like this one is 0 here, then 1, 2, 3, 4, 5, and 6. Okay, so these are like so starting from 0 to 6, so these the display is consisted of 7 segments or 7 LEDs, and by sending uh, uh, sending a 0 to an LED, we can switch it on. Basically, your uh, so this LED is basically active low. So let's say we want to display one here. No, it's not active low, it's active high. So which basically mean that when you send one, the LED will turn on. If you send 0, the LED will turn off. So which means like if it is connected with port C, so first we need to configure the port C in the output mode. So which means writing all ones in DDRC register. And then since based on this numbering, now we know how the connections are. So which means that LED 0 is connected with the pin 0 of the port C, right? And LED 1 is connected with the pin 1 of the port C. So based on that, this we know what value we need to write on the port C. So since we want to write 1, so it means we need to switch on these two LEDs, which are at location or index 1 and 2. So in the port C, we put zeros on all places other than those where we want to send other than those where we want to send a value of 1, right? So at index 1 and 2, basically. This is index 1 and this is index 2. Okay. And this is the corresponding assembly code. So first you are loading 0xFF in R20 register, and then you are sending R20 to DDRC. So these two instructions together, they will configure your port C as output port, and then you are putting this value, which has hexadecimal equivalent of 0x06 in R20 register, and then you are sending R20 to the port C. So now you will see that a value of 1 is displayed on the 7 segment display. Any questions? Okay, now in next example, I really want you guys to do the example on your own. So please give it a try on your notebooks, It is very similar as the last example. The only difference is that we want to display 3 on the 7 segment, right? If you want, I can go back to the previous slide. So just keep in mind that, sorry, just keep in mind that we want to display not 1, 3. So now rework this example so that you can display 3 on the 7 segment. And you have 1 minute to do that. It should be very quick, right? Let me know when you are done. Everything will remain same. You only need to modify the value in port C, right? To display 3 on the 7 segment instead of 1. Okay. So can you tell me what value you are loading in port C? Okay, then let me then go through the code. Okay, someone has finished Salvador. Yeah, you are LXFF. Okay. Yeah, yeah. Okay. Let me go through the code here. See, everything else is same. You are first putting 0xFF in R20 and then sending it to PRC so that can configure port C in output mode. The only difference is what value you are writing to port C, right? So this time what we want to display 3. So if you want to display 3, you need to send one at bit position 0, 1, 2, 3 and 6, right? 4 and 5 are 0, right? So here we are just writing in the port C in these locations 0, 1, 2, 3, and 4, 5, right? And 6 and 7. So what we are doing is that we are sending one at every place other than these two. And this doesn't matter. Why? Remember we said that port C is 7-bit on at Mega 328P, right? So even if it is not, the 7th segment doesn't use the 8th pin. It uses only first seven lines, right? So when you convert this binary into hexadecimal, it becomes 0xf, right? So you are loading 0x4f into R20 and then sending R20 to port C. So then you will see that digit 3 is displayed on the 7 segment display. Okay, so now let's have an example of input, how we can configure a port in the input mode and then read the data from it. So we want to configure port A, which is not available in at Mega 328P, but it doesn't matter. Approach will be same. So configure port A as input and then receive the data from that port and save it in memory at address 0x10, right? So let me walk you through the code here. So Let's say we are simply giving a directive to equate my temp with the address of 0x10, right? Because we want to use this my temp instead of like address in our code. So first what we need to do is that we need to configure port A as input port. So for that, what we are doing is, so what we need to do, so we need to write all zeros in the data direction register of port A, but we cannot directly write data direction register of any ports. So that's why we are first loading all zeros in R16 through our load immediate instruction, and then we are saying, okay, send R16 or write R16 on DDRA register. Now we are done with configuring port A as in input mode. And then we have a NOP instruction, why I will explain, but for time being, just ignore it. And then we are saying, okay, read the data in, read the value from pin A, which is basically, don't confuse it with the pin A. It is basically the pin register of port A. And pin stands for port, port input, right? Port input. So P and IN are combined together to make this pin, right? So this is actually pin register of port A. So read the value from pin A register into R16, and then we are saying, okay, store store to the static memory the value of R16 at address my temp, right? So any questions here other than this knob thing? I will explain it, but other than that, is there any question? Okay, so this knob, this is basically used to accommodate the synchronization delay. And what does it mean by the synchronization delay? Let me uh, explain it on one note here. So what happens is, like, let's say this is your microcontroller, AVR microcontroller, right? And let's say here you have these pins, pin A0 to pin A7, right? And you have configured them as an input, which I'm indicating by putting these arrows, right? So the port is configured. Now the value, the signals of whatever input you are placing on these pins, it is then internally stored in a logic circuit, right? And it takes one clock cycle for these input ports to be latched in this logic circuit. So it takes one clock cycle, right? So if we don't wait for one clock cycle, here it takes one clock cycle, right? If we don't wait for one clock cycle, and after configuring these pins in input mode directly, we immediately want to read the data, so we will have the data available uh, which is older than one clock, right? So previous data, right? So because the data which you are reading is actually you are reading from this output here. So this is like, let's say, your latching circuit, the circuit which stores the value, and here you are reading this. The value you read is becomes available here, our read output, right? Internally in the AVR, right? So it becomes available, the input becomes available, this input becomes available on the outputs after a clock. If you don't wait for a clock and you direct immediately read, then you are not reading the value which is inputted. You are reading the value which was available one clock before, right? Because you are not which was like inputted one clock before, because you are not waiting for one clock after configuring your pins in the input mode, right? So here uh, in this line you are configuring the pin in input mode. And if you don't wait and you say, okay, directly give me the data which is available on pin A, right? So what will happen is that whatever you had older data available on the output of that latching circuitry, it will be made available to you here. whatever you had uh, here, right? Because you are not waiting for one clock cycle, right? So that's why we are putting a knob in between so that one clock cycle is passed, which means that whatever input is, it then becomes available at the output on the internal, sorry, on the in the on the output of the internal latching circuitry. Okay, here we have another example where we are doing both things, input operation, reading input on one port and writing output on another port. So what we want to do is, so the following code, it will get the data present at the pins of the port C and send it to the port B indefinitely after reading the value of 5. So you simply want to read the value from port C, add 5 to it and send it to the port B. And you want to do it in an infinite loop, right? So you need to configure port C in input mode. You need to configure port B as output mode, right? And then read values, add it to it and send to port B. So how you can do this? Here we are simply using directives to equate DDRB with its address 0x04, because let's say we don't want to use the addresses in our assembly. We want to use the name of the registers because it is more readable. So we are doing same thing for port B, DDRC, pin C register and port C register, right? So first, we need to configure port C in input mode. So how we can do that? By sending all zeros to the data direction register of port C. So what we are doing is that we are first loading 0 in R16 and then we are saying write R16 to the data direction register of port C. So now port C is configured as input port. But remember we said that if you are not working with analog to digital conversion, but you are simply reading digital inputs, once you want to read simple digital inputs, then it's always recommended to turn on the pull-up registers. So for that, what we need to do is to like enable the pull-up registers, would need to write ones on the port C register, right? So that's why we are first loading 0xFF in R16, and then we are saying write the value of R16 on the port C register. Now all the N input internal pull-up registers on the port C, they will be enabled, right? If you have questions, let me know. And after that, what we need to do is that we need to configure port B in output mode. So for that, we are writing R16 on the data direction register of port B. Remember, R16 already has the value of 0xFF. And when you write all ones, which is basically all ones, when you write all ones on the data direction register of port B, it's mean you have configured all the pins of that port in output mode, right? Uh, and then what you need to do is that you need to read the value from the port C and send it to the port B. But how we read the value from the ports from any given port? By reading its pin register. That's why we are reading the pin register of port C and putting the value and read it into the R16, right? And after that, what we are doing is that we need to add 5 to that value which we have read from port C. So we are loading 5 in R17 using load immediate instruction, adding R17 to R16. So we have the result in R16 available. And then we need to send it to the port B. So we already have configured the port B in output mode. Now we can simply write the value or the result after addition in the port register of port B, right? So that we are done with that, and now we can do the relative jump to make an infinite loop. Any questions? Okay. Here we have another example, which is about again output, sending the output. So we want to write a program which continuously sends out to the port C the alternating values of 0x55 and 0xAA, right? It is straightforward again. Simply, we are using the equate directive to set DDRC equal to 0x07, which is address of the DDRC register basically, and port C we are equating it with 0x08, which is address of port C register, right? So if we want to write port C, we first need to configure it. So how we configure it in output mode? By writing all ones. So we are putting 0xFF in R16 and then sending R16 to DDRC. Now we are done with configuring the port C in output mode, and then we first want to send 0x55 on the port, on the output, right? So we are loading 0xFF in R16, and we are writing R16 to port C. After that, it will be better to put a delay here so that, like, for example, if you have LEDs connected on the output, you can see that, okay, they stay, you can monitor the values. Then you are putting 0xa in R16 and sending R16 to the port C. So basically, you will be simply toggling the values, and then you are taking the jump to go back, and it will make an infinite loop. Okay, any questions here? Okay, until this point, we have talked about ports and and how we can, like, manipulate the whole port as a single entity. For example, we saw how we can configure all the pins of a port, for example, port C in input mode or output mode. But what about if I don't want to configure all the pins of a port as input or as output? Or in other words, let me go back to the uh, one note again and uh, try to visualize what I mean. So let's say you have this, again, you have AVR microcontroller, and you have these pins here. Let's say pin B0 to pin B7, port B7, right? And let's say I want to use first four pins as input pins, and the next four as output, right? So can I do that? Like, or even like, for example, let's say I want to do it in an alternative order, like first pin as input, the next one as output, next one as input, next one as output, and so on. So which basically mean that, can I uh, do the configuration at pin level instead of the port level, right? So yes, we can do that in the AVR microcontroller, but for that we need the instructions which manipulate bits of the register instead of the whole register, right? So first instruction, which does the bit manipulation, is set bit in IO register. So the syntax is that you provide the name of the instruction and then the name of the IO register, uh, and the bit within the IO register which you want to set. So here basically you are saying that set this bit of the IO register equal to one. So the example is, if you say set bit in IO register port D0, so basically you are saying, like, port D is, remember, in 8-bit register, right? So you are saying that set the bit at index 0 equal to 1, right? And in the next instruction, set SBI, let me call it as SBI DDRC5. So what you are necessarily saying is this, like, let's say this is your DDRC register and it has 8 bits. So you are saying set the bit at index 5 equal to 1. So you are, like, changing the value. You are changing the value of only a single bit. All other bits in the register, they will remain unchanged. Whatever the value had previously, they will retain those values. So this is the format of its machine code or binary code. So you have 1001 and 1010 as its opcode. So these 8 bits together make the opcode. From the significant side, if you read the first 3 bits, they are used to specify the index of the bit, because there are 8 possibilities. So you need 3 bits to specify the index of the bit, and the next 5 bits, they are used to specify the register, and the register can be the lower 32 register in the IO address space. Remember, I am saying lower 31 registers in IO address space, which means which means that you cannot use this with the general purpose registers. And it is also clear from the name, set bit in IO register, right? So you cannot use this instruction for, so for example here, if you write R0, then your assembler will complain. Okay. Clear bit, this is actually opposite of SBI instruction. So here you are saying, instead of setting clear the bit in IO register, and everything else, our syntax is same. So here you provide the index of the bit and here the name of the register. So for example, if you say here CBI port D, comma 0, so basically you are saying that I have 8-bit register port D, and clear its bit at the index 0. So we don't know what was the older value, but the new value after this instruction at the bit index 0 will be 0. And CBI 5, DDR5, DDRC5. So basically, again, it means like set the bit at index 5 equal to 0 for the DDRC register. And here you have this 8-bit opcode for the instruction. And then again, the last three significant, least significant 3 bits, they are used to specify the bit index. And these next 5 bits, they are used to specify the register name. And again, the register can be the lower 32 registers in the IO address space. Any questions? Okay, so let's have a look at an example how we can use these instructions. So let's say we want to write a program that toggles the port B.4 continuously. Note this is different from what we had earlier. Earlier we were toggling the value on the whole port. This time we are saying we have this pin B on the AVR microcontroller and the pin B4. So we want to toggle value only on this pin. All other values on all other pins, they remain unaffected or unchanged, right? We don't, and even maybe, so basically we are saying we want to configure it as the output and then write on this pin 0, or first 0 then 1 then 0 then 1, right? And other pins, I don't know, I mean, we don't care, maybe they are configured as input or output. We are not concerned with that, right? So how we can do that? Again, we are simply using equating DDRB to 0x04, which is address of DDRB register, and we are equating port B to 0x05, which is address of port B register. But here, this time, what we are doing is that first we are configuring only this pin in the output mode, right? So how can we configure? By writing 1 in the 4th bit of DDRB register, right? So that's why we are saying set the bit number 4 in the IO registered DDRB, right? So after configuring, we need to want alternatively send 0, then 1, then 0, then 1, and so on, right? So first, let's say we want to set 1. So how we want to, how we can send a value on the port after configuring it in output mode? By writing in its port register. So, but this time we are using the bit manipulation instruction. So what we need to do, we need to write 1 in the port B register, but at index 4, right? So I don't want to write the full name here, but this is port B register. So what we are saying is that set the bit at index 4 of the port B register. So it will be set equal to 1. And then after that, we want to send 0. So we simply need to replace it with 0. So which means we want to clear this bit. So we are saying clear the bit at index 4 of the register port B. And then we are jumping back to make an infinite loop. Okay. Any questions? Okay. So uh, I was thinking whether I should ask you to do this example. Let me walk you through this example because You have seen until now only one example of using the SPI or CBI instruction, right? So let's say that LED is connected, and LED is connected to each pin of the port D. And now we want to write a program to turn on each LED from pin D0 to pin 7. But between, like, what we need to do is that we want to put a delay module, or we want to put the delay before turning on the next LED. So basically what we are saying is that from PD0 to PD7 we have connected LEDs on the output, and we want to switch them on one by one. So after switching the LED 0, we wait for some time, and then we switch on the LED 1, then wait, and then LED 2, and so on. So how we can do this? Actually, very straightforward. So we are using these equate directives to equate DDRD with 0x0A, which is actually address of DDRD register, data direction register for port B, port D. And we are equating port D to 0x0B again, which is address of the port D register. And first we need to configure this whole port in the output mode, right? So we are loading 0xFF in R20, and then we are sending R20 to 0 DDRD0. Now we are done with the configuration of the port in output mode. And after that, what we need to do is that we first need to we need to send only one on this line, right? But not on the other pins, right? So what we can do is can say, okay, how we send one by writing by writing 1 at index 0 of the port D register. So this is what we are doing here. So we are saying set the bit at index 0 of port D, and then call delay. So wait for some time, and then we say, okay, set bit. So we keep doing the same thing for other lines by setting the next bits equal to one by one, right? In sequential order. So set the bit and index 1 for the port D equal to 1, right? And then again delay. And then set the bit at index 2 in the port D register, and then delay, and so on, right? Any questions? No? It looks like the lectures are becoming super easy, or I am becoming how to say, uh, very good at my teaching skills. There were no questions today. Anyway, so today you have a quiz. So you have like yeah, 2 minutes before the quiz start. So please proceed to Canvas, log in, and uh, start doing the quiz released or becomes available. But I am here until end of the lecture time. Okay, I'm just muting my.